Okay, hi guys. Sorry for the delay. Actually, there was a network issue. So I will share my screen. One of you can unmute and let me know if my screen is visible and if I'm audible. Just give me a second. Yeah. Can one of you unmute and let me know if my screen is visible and if I'm audible?
Yes, ma'am.
Okay. Thank you. So yeah. So good evening, everyone. So today we'll be doing the week 5 of the session on fundamentals of protein chemistry. Basically, so in these live sessions, what we do is that we basically talk about uh, this course and some of the old assignments of this course, right? So we will not only discuss the assignment questions, we'll also discuss the concepts behind those questions so that it's easier for us to solve similar type of other questions, right? So that's basically the motive of this live sessions. My name is Vaishya. I'm a PhD scholar from IIT Bombay, and we'll start today's session. So before we start, we try to keep it as interactive as possible. So if you have questions, you can just unmute yourself and let me know, or maybe type in the chat box. If I know the answer today, I will definitely answer today. If I don't, then I'll read about it and let you know by the next class. Right? And at the end of the sessions, I will upload all these videos, recordings, along with the slides. The videos will be uploaded on YouTube. So going on to the first question for today. One second. Yeah. So an amino acid has a sorry. So I will just read the question once. So the question is, an amino acid has a pKa of 2.8 for its carboxyl group and a pKb of 9.6 for its amino group. At which of the following pH values will this amino acid have a net positive charge and migrate towards the cathode? The options are A 3, B 6.2, C 8.5 and D 11. So I will wait for a few minutes as you figure out the answer. You can you have to explain the answer as well in detail from scratch. So anybody would like to take up the question? You can try to calculate it if you have a pen and paper in front of you. You can just try to calculate it. Then we'll move ahead. Anybody? someone type, I think, was there? Yeah. Okay. Did anybody type A? Okay, let me see what A is. So you mean 3? Okay. You might be right. Can you explain why it's 3? Okay. Okay. Okay, so we'll start discussing. You're right, it's 3, and we'll get to where how we come to the answer. So first we'll discuss a little bit about this dipolar ions isoelectric point electrophoresis. We have discussed a lot about isoelectric point in case of amino acids, but we have not discussed about electrophoresis and how basically these kind of experiments are carried out in the lab. So, if you see the physical properties of a typical amino acid, such as glycine, suggest that it is a very polar substance, much more polar than would be expected on the basis of its formulation. Right? So, when measured in aqueous solution, the dipole moment of glycine is 14. Okay, that's the unit, and is found to have a large value. To account for this large value, it has been suggested that glycine exists in solution as an inert salt, and therefore it is to some extent ionic in nature. Right? So, such a double charged ion is also known as a Zwitter ion, amphorite or dipolar ion. So glycine is a crystalline solid. If you have seen glycine in labs, we use glycine in SDS page, Western blots. I think glycine is used for as transfer buffers in Western blots. So it's basically a crystalline solid. It does not melt, but on being heated, it eventually decomposes at 233 degrees Celsius. It's very soluble in water, practically insoluble in nonpolar organic solvents. So these properties are attributed to the fact that the stable form of glycine is a Zwitter ion or inert salt. Okay, now the dipolar ion structure also accounts for the absence of acidic and basic properties of an amino acid. That the carboxyl and the amino groups of the same molecule neutralize each other to form a salt. The properties of crystalline glycine, that is its melting point and its insolubility in hydrocarbon solvents, also indicate that it exists as the inner salt in the solid state. So, X-ray analysis has shown that all amino acids exist as dipolar ions. Now, the dipolar moments of the amino acids are comparatively higher than those of amines and carboxylic acids of similar molecular weight, right? Like 1.7 dBi for propionic acid and 1.4 dBi for N-butylamine. Now, glycine as well as other amino acids is amphoteric, meaning it contains an acidic functional group and a basic functional group. And the acidic functional group is the aminium ion NH3 plus, and the basic functional group is the carboxylate. So amino acids contain both. Sorry, I said opposite. I hope you understand. The acidic functional group will be carboxylate, and the amino acids contain both a basic group and an acidic group. Now, consequently, in the dry solid state, amino acids exist as dipolar ions, right? So, a form in which the carboxyl group is present as a carboxylate ion and the amino group is present as an aminium ion. Now, dipolar ions are also called Zwitter ions. So, in aqueous solution, an equilibrium exists between the dipolar ion and the anionic and the cationic forms of amino acid. So this is dipolar ion. This is a cationic form predominant in strongly acidic solutions like lower pHs. This is the anionic form predominant in strongly basic solution like pH closer to 14. Okay. So in an electric field, basically, cations or the net positive charge will migrate towards the cathode. It is negative, and a simple amino acid, no ionizable side chain can exist in three main forms as the pH changes. We'll come to that. Now, the position of the equilibrium as also the predominant form of the amino acid present in a solution depends on the pH of the solution and on the nature of the amino acid. So, in strongly acidic solutions, all amino acids are present primarily as cations, that is, the conjugate acid predominating, and in strongly basic solutions, they are present as anions, that is, the conjugate base predominating. So for each amino acid, there is a particular pH value at which the concentration of the dipolar ion is a maximum. Now the isoelectric point is the pH at which the concentration of the dipolar ion is at its maximum and the concentrations of the anions and the cations are equal. So each amino acid has a particular isoelectric point. Now proteins have isoelectric points as well, and this property of protein is important for their separation and identification. Very important. Now since the net charge is zero, the dipolar ion is electrically neutral, and consequently in this condition the amino acid does not migrate when placed in an electric field. Now, since they can both behave as an acid and a base, monoamino monocarboxylic acids have two pKa values, one as an acid when titrated with base and other as base when titrated with an acid. So, by convention, pKa1 is the one corresponding to the group titrated at the most acidic region, that is the carboxyl group, and the change is from the carboxylate ion. So the isoelectric point of an monoamino monocarboxylic acid can easily be calculated. If this isoelectric amino acid is represented as this, then this equilibrium exists. Okay. So if you see this, there are two equations. From here, if we move on to the anions and the cations, and if we see there are two equations, so from equation 1 we get this, from dipolar ion plus H plus by the product by the reactant, and in case of equation 2 we get this, again the product by the reactant. So as an isoelectric point Pi, this is maximum, and since the net charge is zero, this is the equation that we come up with. Okay, so therefore for monoacidic and monobasic amino acids, isoelectric point is the average of the pKs of the monocation and the dipolar ion that we can see over here. So the isoelectric point is basically at which the net charge will be zero, and for this the isoelectric point of glycine can easily be calculated from this data which has been given. So if pKa1 is 2.4 and pKa2 is 9.6, this will be 6. The isoelectric point of glycine will be 6 from this, 2.4 plus 9.6 by 2. So pKa1 corresponds to the ionization of the carboxyl group, and pKa2 corresponds to the deprotonation of the ammonium ion. Now, if you consider first an amino acid with a side chain that contains neither acidic nor basic groups, like a neutral amino acid such as alanine. So, if it's dissolved in a strongly acidic solution, it is present in mainly a net cationic form, right? And in this state, the amino group is protonated. It bears a formal +1 charge and the carboxylic acid group is neutral. It has no formal charge. So, as is typical of alpha amino acids, the pK for the carboxylic acid hydrogen of alanine is considerably lower than the pK of the ordinary carboxylic acid, like if we consider an acid like propanoic acid. So, the reason for this enhanced acidity for a carboxyl group in an alpha amino acid is the inductive effect of the neighboring aminium ion, which helps to stabilize a conjugate base, a carboxylate anion formed when it loses a proton. So, loss of a proton from the carboxyl group in a cationic alpha amino acid leaves the molecule electrically neutral in the form of a dipolar ion. So, this equilibrium is shown in the left side of the equation in figure 3 here. So the protonated amino group of an alpha amino acid is also acidic, but less so than the carboxylic acid group. So the pKa of the aminium group in alanine is 9.7, and the equilibrium for loss of an aminium proton is shown in the right side of this equation. So the carboxylic acid proton is always lost before a proton from the aminium group is an alpha amino. So this is the acid-base equilibrium of a neutral amino acid. So the state of an alpha amino acid at any given pH is governed by a combination of two equilibria as shown in this equation. So for the alanine pi or isoelectric point will be the average of pKa1 and pKa2, right? Now, when a base is added to a solution of the net cationic form of alanine, the first proton removed is the carboxylic acid proton, as is expected, right? And in the case of alanine, when a pH of 2.3 is reached, the carboxylic acid proton will have been removed from half of the molecules. And this pH represents the pKa of the alanine carboxylic acid proton, as can be demonstrated by the Henderson-Hasselbalch equation, which shows that for an acid, HA and its conjugate base A minus, when HA is equal to A minus the concentration, then pH will be pKa, right? So pH is basically pKa minus log A minus by HA. So therefore, when the acid is half neutralized, that is the concentration of HA and A minus is equal, log A minus by HA is 0, and thus pH equal to pKa. Now, as more base is added to the solution, alanine reaches its isoelectric point, and the pH at which all of alanine's carboxylic acid protons have been removed, but not its aminium protons. So the molecules are therefore electrically neutral in the dipolar and ionized butyrionic forms, because the carboxylate group carries a -1 charge and the aminium group carries a +1 charge. So the pi for alanine will be 6. Now, on continuing the addition of base, protons from the aminium ions will begin to be removed until at pH 9.7 half of the ammonium groups will have lost a proton. Now, this pH represents the pKa of the aminium group. Finally, as more base is added, the remaining aminium protons will be lost until all of the alanine molecules have lost their aminium protons. So, at this point, the molecules carry a net anionic charge from the carboxylate group, and the amino groups are now electrically neutral. So a titration curve for this equilibrium is shown in the next figure I'll show. So the graph represents a change in pH as a function of the number of polar equivalents of base, and because alanine has two protons to lose in its net cationic form, when one molar equivalent of base has been added, the molecules will have each lost one proton and they will be electrically neutral. Now at pH values less than pKa1, this is the major species present, right? And at pH values between pKa1 and pKa2, the principal species is the azitrion, which is the net charge is 0. Now the concentration of the zwitterion is a maximum at the isoelectric point, and the pH greater than pKa2. This is the species which is dominant in the greatest condition. This is the acid-base equilibrium of glycine. So if an amino acid contains a side chain that has an acidic or basic group, the equilibrium will become different. So let us consider lysine, for example, an amino acid that has an additional NH2 group on its epsilon carbon in addition to the alpha NH2, and in strongly acidic solution lysine is present as a dication because both amino groups are protonated. So the first proton to be lost as the pH is raised is a proton of the carboxyl group. The next is from the alpha aminium group, and the last is from the epsilon aminium group. Okay, 2.29 and 10.5. This is the equilibrium for lysine. So the isoelectric point of lysine is the average of pKa2 and pKa3. This therefore corresponds to the equilibrium among the monocation and the monoanion with the dipolar ion. So therefore the isoelectric point of lysine will be 9 plus 10.5 by 2, which is 9.8. Okay. So the isoelectric point of the amino acids are basically midway between the pK values of the conjugate acid, that is the monocation, and its dipolar ion, that is the zwitterion. So aspartic acid has an acidic side chain and therefore a pI of 2.77. The pKa1 and pKa2 values are 1.88 and 3.65 respectively. Okay, so the acidic amino acids aspartic and glutamic acid have acidic side chains, and basic amino acids like lysine, arginine and histidine have basic side chains, and individual amino acids differ in their acid-base properties. So this is important in peptides and proteins where the properties of the substance depend on its amino acid constituents, especially on the nature of the side chains. Now if we come to the process technical, we have talked about theory. If we come to the practical process, electrophoresis is a method of separation and purification that depends on the movement of charged particles in an electric field. So its principles can be introduced by considering the electrophoretic behavior of some representative amino acids. So the medium is basically a cellulose acetate strip that is moistened with an aqueous solution buffered at a particular pH. So the opposite ends of the strip are placed in separate compartments containing the buffer, and each compartment is connected to a source of direct electric current. So if the buffer solution is more acidic than the isoelectric point of the amino acid has a net positive charge and migrates towards the negatively charged electrode or the cathode. Conversely, when the buffer is more basic than the pI of the amino acid is in net negative charge and migrates towards the positively charged electrode, the anode. So when the pH of the buffer corresponds to the pI of the isoelectric point, the amino acid has no net charge and does not migrate from the origin. So if a mixture containing alanine, aspartic acid and lysine is subjected to electrophoresis in a buffer that matches the isoelectric point of alanine, that is pH 6, aspartic acid pI 2.8, it migrates towards the positive electrode. Alanine remains at the origin and lysine migrates toward the negative electrode. That is how the entire process of electrophoresis works out. Right? Alanine with a net charge 0 will happen at pH 6. Lysine will happen at 9.7 and aspartic acid at 2.8. Now, a mixture of amino acids, alanine, aspartic acid, and lysine is placed at the center of a sheet of a cellulose acetate. Okay, the sheet is soaked with an aqueous solution buffered at a pH of 6. At this pH, aspartic acid exists as -1 ion, as an anion. Alanine as its dipolar anion, that is zwitterion. it is at its isoelectric point, so the net charge is 0. And lysine as its plus 1 ion as a cation, as shown in this figure. So application of an electric field will cause the negatively charged ions to migrate towards the positive electrode and the positively charged ions to migrate towards the negative electrode. And the dipolar ion with the net charge 0 will remain as it is in its original position. Okay. So results of the electrophoresis of alanine, aspartic acid and lysine at buffer pH 6.0. Alanine will be neutral, negative net charge 0, so no movement. Aspartic acid neutral at pi, so mode and net charge -1, movement towards positive electrode or anode. And lysine monocation net charge +1, movement towards negative electrode or cathode. Okay. However, the success of this method in separating mixture of amino acids depends on the nature of the amino acids as well as the pH of the buffer medium. So, complete separation of these three amino acids cannot be possible if the sheet is soaked with an aqueous solution buffered at a pH which is equal to the pI of the either aspartic acid or lysine. Right? In that case, it might not be possible. So at pH 2.8, which is equal to the pI of the aspartic acid, it will exist as a dipolar ion. That is, aspartic acid will be a zwitter ion and hence it will be electrically neutral and will not migrate under the application of electric field. However, alanine and lysine both will exist as +1 ion and +2 ion respectively. Like alanine will be +1 ion, lysine will be +2 ion. Therefore, both of them will migrate towards the positive electrode cathode. Consequently, alanine and lysine will not be separated. On the other hand, at pH 9.7, which is equal to the pI of lysine, the latter, like lysine, will exist as dipolar ion or zwitter ion and hence will not migrate because it will be electrically neutral. Right? And it will not migrate under the application of electric field. However, aspartic acid and alanine will exist as -2 ion and -1 ion respectively. So therefore they will migrate towards the negative electrode anode. Okay. Consequently, basically they will migrate towards a positive electrode anode. Sorry. This will be opposite. Consequently, aspartic acid and alanine cannot be separated. One second. The negative electrode, negative ion, positive ion is cation, negative electrode is cathode, negative electron, negative ion is anion, and positive electrode is anode. You get confused between these two very frequently. Yeah. So again, if the mixture contains two or more amino acids of the same type, such as neutral or acidic or basic, separation under this method cannot be possible. So electrophoresis is basically used primarily to analyze mixture of peptides and proteins rather than individual amino acids, but analogous principles apply because they incorporate different numbers of amino acids and because the side chains are different, two peptides will have slightly different net charges at a particular pH. Thus, their mobilities in an electric field will be different and electrophoresis can be used to separate them. So, the medium used to separate peptides and proteins is typically a polyacrylamide gel, leading to the term gel electrophoresis for this technique. Now, if you talk about amino acid titration at physiological pH, the carboxyl group of the amino acid is negatively charged and the amino group is positively charged. So, without charged side chains, it will be zwitter ions and have no negative charge, no net charge. Now, a titration curve shows how the amine and the carboxyl groups react with hydrogen ion. Now at low pH, a non-acidic or non-basic amino acid is protonated and has a structure below. Okay. Now the charge behavior of acidic and basic amino acids is more complex. The isoelectric point for an amino acid occurs when there is no net charge. For a neutral amino acid, the pI is calculated using this equation, pKa1 plus pK2 by 2. So for alanine, 2.34 plus 9.7 by 2, 6. So for basic or acidic amino acids, the pI is the average of the two pKa values bracketing the isoelectric structure. Now in general, the pI is the average of the two pKa's bracketing the structure, like glutamic acid is over here. Okay, so pKa1 2.2, pKa2 4.3 and pKa3 will be 9.9 for glutamic acid. Now peptide is written with the N terminal N to the left and C terminal N to the right. We know that, right? So for this peptide, it will be tyrosyl, alanine, cysteine, glycine, and then the peptide bond is rigid and planar due to the resonance contribution shown. The peptide bond angles for specific conformations of proteins around the extended chains, successive R groups are on opposite sides. Now this is a titration of glycine with NaOH. pKa1, pKa2, pi sorry, and pKa2. Pi is isoelectric point. As I said, it's a pH at which the majority of amino acid molecules in solution have no net charge. So the pi for glycine, for example, falls under the pKa values for the carboxyl and amino groups. So these are the pi values of most of the amino acids, protein derived amino acids. Acidic basic side chains. So electrophoresis is basically the art of separating compounds on the basis of the electric charge. It can be carried out using paper, starch, agar, certain plastics and cellulose acetate as solid supports. In paper electrophoresis, a paper strip saturated with an aqueous buffer of predetermined pH serves as a bridge between the two electrode vessels. So sample of amino acids is applied on a spot on the paper strip. An electric potential is applied to the electrode vessels and the amino acids migrate towards the electrode with charge opposite to their own. So molecules with a high charge density move faster than those with a low charge density. So molecules at the isoelectric point remain at the origin. After separation is complete, the strip is dried and developed to make the separated amino acids visible. An reagent commonly used to treat amino acid is ninhydrin. So if an alpha amino acid reacts with ninhydrin, it forms a purple colored anion. So coming to the question that we started with, for a conjugate acid base pair at 25 degrees Celsius, pKa plus pKb will be 14. Okay, so if pKb is 9.6, so pKa will be 14 minus 9.6, 4.4. So basically we now have pKCOOH 2.8 and pKaNH3 will be 4.4. Okay. So if you have to find the isoelectric point, we will take 2.8 plus 4.4, which will be 7.2 by 2, 3.6. So at pH lesser than 3.6, the net positive will be, it will be net positive, it will migrate towards the cathode, the negative electrode. For pH greater than 3.6, it will be net negative and it will migrate towards the anode, the positive electrode. So among the options, only pH 3 is below 3.6, right? So it predicts net positive. So that's why the answer to this question will be 3. Okay. Anybody has any questions? Queries regarding this question? I'll stop for a few minutes, then we'll move on to the next question for today. Any queries, anyone? I'll wait for a few minutes, then we'll move on to the next question for today. Anybody? Okay, moving on to the next question for today. Which statement about peptide bond among the following is incorrect? It is stronger than an ordinary single bond. Rotation around the peptide bond is restricted. It is a major chromophore in the far UV region, and it shows a weak absorption band around 190 nanometer and a strong band around 220 nanometer. These are statements 1, 2, 3, and 4. And the options are A 1 and 2, B 2 and 3, C 3 only, and D 4 only. Anybody? Okay, so if anybody wants to try, I can wait a little longer or we'll move ahead to the answer. Okay, so the answer will be 4 only. We'll discuss the. So we have talked about peptide bonds a lot, right? So the amino acid sequence from N to C terminus determines the primary structure of peptide or a protein, and the amino acids are linked together through amido peptide bonds. We know that. Now, the CN distance in a peptide bond is typically 1.32 angstrom, which is intermediate between the values expected for a CN single bond, 1.49 angstrom, and a CN double bond, 1.27 angstrom. Now, cis-trans isomerism, if having a partial double bond character, the peptide bond is planar. So, for steric reasons, the trans configuration is normally favored in peptides and proteins. Only rarely are cis peptide bonds seen in natively folded protein crystal structures. Now, proline is an exception where the proportion in the cis form is larger. Okay, and the energy differences have been estimated in small model peptides. Now, if we talk about peptide conformation, backbone conformation, in order to describe the backbone conformation of a peptide or protein, it is necessary uh, to define the torsion angles phi, psi, and omega for each residue. Now, the angle of rotation about the bond between the nitrogen and the alpha carbon atoms is called phi, and the angle of rotation about the bond between the alpha carbon and the carbonyl carbon atoms is called psi. Now, a clockwise rotation about either bond is viewed from the front to the back group corresponds to a positive value. The torsion angle is 0 when the neighboring backbone atoms are in cis conformation. So when the backbone atoms are trans anti-periplanar, the torsion angle is 180 degrees Celsius. 180 degrees, sorry, not Celsius, 180 degree. Now, backbone conformation in 1951, Linus Pauling and Robert Corey proposed two periodic structures for polypeptides called the alpha helix and the beta pleated sheath. They hypothesized that preferred backbone torsion angles for phi and psi in polypeptides would give rise to these secondary structures. Now, G. N. Ramachandran catalogued all combinations of phi and psi forbidden because of steric collisions between atoms. He showed that the allowed values can be visualized on a two-dimensional plot, which became known as the Ramachandran plot. Now, the classic example showing the allowed regions for all amino acids over here, except glycine and proline, is shown below. Over 3/4 of the possible combinations are excluded simply by local steric clashes. And in the allowed regions, the dihedral angles characteristic of the three common secondary structures are found. Okay. We have talked about Ramachandran plot also in a previous class. Now, if we talk about the secondary structures, alpha helix, H bonds are found between the carbonyl CO atom of residue N and NH of residue N plus 4. And the overall helix therefore has the dipole moment aligned along the helix axis, which is positive at the N terminus and negative at the C terminus. This microdipole can be stabilized by capping the N and C terminus and or by placing acidic residues at the N terminus and basic residues at the C terminus. The tendency of a peptide chain to adopt helical secondary structure depends on its amino acid sequence and length. Now, beta sheets are also predicted by Pauling and Corey. The first example was seen in the structure of hen egg white lysozyme. In a beta sheet, two or more polypeptide chains run alongside each other and are linked in a regular manner by hydrogen bonds between the main chain CO and NH groups. Therefore, all hydrogen bonds in a beta sheet are between different segments of polypeptide. This contrasts with the alpha helix where all hydrogen bonds involve the same element of secondary structure. Now the side chains of neighboring residues in a beta strand point in opposite directions. The complex interactions between the secondary structures that drive protein folding are typically mediated by hydrophobic interactions. Interestingly, the isolated secondary structures from most proteins are not usually stable outside the context of the protein. Now, biomimetic chemistry, one important direction in chemical biology is the development of small molecules or constrained peptides used to mimic small regions of folded proteins. If we talk about proline, this cyclic residue can only adopt a very limited number of stable conformations. It is known as the helix breaker, alpha helix breaker, as none of these conformations are compatible with the alpha helix. And polymers of proline in water adopt a left-handed polyproline type 2 helical conformation, a secondary structure found in 50% of the proteins and possibly the predominant conformation of denatured proteins. If we talk about polyproline helices, type 1 helix is observed in organic solvents. Polyproline in water adopts a type 2 helix. The type 2 helix is a common secondary structure observed in many other proteins too. Unfolded proteins often exhibit CD data consistent with type 2 structure. Now, CD structure of poly-L-lysine in alpha helical antiparallel beta sheet and extended conformation. Placental collagen in its native triple helical and denatured forms. Note that the extended conformation of poly-L-lysine was originally described as a random coil, but its spectrum is similar to the conformation of poly-L-proline, which forms an extended left-handed helix. Now, disulfide bond formation in secreted proteins, disulfide bonds between cis residues help to maintain the protein's tertiary structure. Okay, so peptoids basically are synthetic poly and substituted lysines are a class of peptidomimetics whose side chains are appended to the nitrogen atom of the peptide backbone. Peptides with the alpha chiral bulky side chains are known to adopt a polyproline type 1 like conformation. Now, if we talk about cyclization, many natural peptides and man-made mimetics are backbone or side chain cyclized. This natural product, alpha-amanitin, is a potent inhibitor of RNA polymerase 2. Now, if we talk about beta peptides, which are also synthetic, they consist of beta amino acids. Many types of helix structures consisting of beta peptides have been reported. These conformation types are distinguished by the number of atoms in the hydrogen bonded ring that is formed in solution. 10 helix, 12 helix, 14 helix have been reported. Generally speaking, beta peptides form a more stable helix than alpha peptides. Now we know about dipeptide or more amino acids covalently joined by peptide bonds. Two amino acid molecules can be covalently joined by peptide bond to yield dipeptide. This linkage is formed by removal of the element of H2O from the alpha carboxyl group of one amino acid and alpha amino group of the other by the action of strong reducing agents. Now, three amino acids can be joined by two peptide bonds to form a tripeptide. When there are many amino acids joined in the same way, the structure is called a polypeptide. The total acid-base behavior of a peptide can be predicted from its single free alpha amino group at the end of the chain, its single free alpha carboxyl group at the end of the chain, and the nature and the number of its ionizing R groups. Peptides have a characteristic isoelectric point. Peptides have characteristic titration curves. Complex mixtures of peptides can be separated from each other by ion exchange chromatography or electrophoresis. Now, peptides have characteristic chemical reactions. These reactions are characteristic for functional groups. Their peptide bonds can be hydrolyzed by boiling with either strong acid or base to yield the constituent amino acid in free form. And peptide bonds can also be hydrolyzed by proteolytic enzymes secreted into the intestine for protein digestion, like trypsin and chymotrypsin. Trypsin cleaves the peptide bond on the carbonyl side of arginine and lysine. Chymotrypsin cleaves the peptide bond on the carbonyl side of phenylalanine, trypsin, and tyrosine. Tryptophan and tyrosine. Now, we'll not go into the reactions. We have talked about the protein backbone, the biochemical view. You can also look at repeating units from C alpha to C alpha. Bond lengths are almost equal in all groups in all proteins, and bond angles almost equal in all groups in all proteins. All C alpha atom belongs to 2 units, and all atoms in a unit coplanar. Okay. So a sulfur atom and carboxyl group of residue 1 I and amino group and C alpha atom of residue Y plus 1 are rigid groups. Rotation on bond CN is prevented by energy barrier. Now peptide units are joined by covalent bonds between C alpha atoms, and thus peptides can rotate along two bonds NC alpha and CC alpha C. Two dihedral angles for each unit phi and psi, 2 degrees of freedom per unit, determine the conformation of the backbone. Repeating units of phi and psi along the main chain result in regular structure. Repeating values of phi and psi give a right-handed helical fold. Repeating values of psi and phi give subchains with conformations that allow interactions between nearby parallel segments. Most combinations of phi and psi angles are not allowed. Allowed conformations plotted as 2D chart. Now defined by patterns of hydrogen bonds between backbone amide groups, side chain, main chain and side chain hydrogen bonds are irrelevant. The amino acids in the interior core of a globular protein have hydrophobic side chains. Water-soluble proteins fold to pack hydrophobic side chain into interior, results in hydrophobic core and hydrophilic surface. The main chain must fold into interior too. Main chain is hydrophilic, NH hydrogen bond donor, C double bond O hydrogen bond acceptor. So these groups must be neutralized by formation of H bond secondary structure. Secondary structure alpha helices, beta sheets, they form stable and rigid frameworks. We have talked about alpha helix, it's a right-handed coil formation A backbone NH group of I plus 4 forms hydrogen bonding with backbone C group I. 3.6 residues per turn. Okay, variations with side chain more loosely or tightly coiled are possible, but not often. Backbone dihedral angles around -60, -45. Sum of phi and psi angles of consecutive residues about 105 degree. Has between 4 to 40 residues. All H bonds point in the same direction. Aligned along helical axis. Dipole moments for residues are aligned along the axis. Net dipole for alpha helix. Beta sheets combination of several regions of the chain, not chain adjacent. Beta strands parallel. All amino acids go in the same direction, evenly spaced H bonds. Anti-parallel amino acids in successive strands alternate directions, alternate narrowly widely spaced H bonds. Mixed beta sheet also exists. They have twisted strands, right-handed twist. Beta strand 5 to 10 residues long, almost fully extended. A protein structure built from secondary structures connected by loop regions, various lengths, irregular shape are the surface of the protein, rich in charge and polar residues. In homologous proteins, almost always insertions and deletions occur in the loop regions. Secondary structures connected to form motifs, alpha helices and beta sheets in a motif adjacent in the three-dimensional structure connected to loop regions, combinations of motifs and secondary structure domains. A tertiary structured arrangement of secondary structural domains, quaternary structure more than one polypeptide folded together, native conformation, direct consequence of primary structure, chemical environment, water-based oily interior of a cell membrane. So far, no reliable computational method exists to predict the native structure from the amino acid sequence. So basically, protein structure can be alpha domains, core built from alpha helices, beta domains, core built up from only usually two antiparallel beta sheets, alpha beta domains, mostly beta alpha beta motifs, mostly parallel beta sheets surrounded by alpha helices, alpha plus beta domains, antiparallel beta sheet packed against alpha helices. So properties of amino acids are capacity to polymerize, novel acid-base properties, varied structure and chemical functionality, chirality. So examples and functions of proteins can be enzymes, biological catalysts that are vital to all living systems. They are simple or conjugated proteins, proteins that fold living systems together, such as collagen, proteins that act as messengers, such as insulin, proteins that carry molecules and ions from one place to another in the living system, such as hemoglobin, and proteins that destroy any foreign substance relations to the living system by an infectious agent, proteins that are poisonous. This is a basic amino acid structure. We have discussed all about this. Amino acid classification, enantiomer, they are basically stereoisomers and enantiomers. Biological system can only synthesize and use L amino acids. Aliphatic, aromatic, sulfur containing, polar, uncharged, basic, so they can be hydrophobic or hydrophilic. The peptide bond formation is shown here with the release of water. The thiol side chain is oxidized by the oxygen in air of oxidizing agent to form two cysteine molecules. So basically, the statement among this which is incorrect that it shows a weak absorption band around 190 and a strong band around 220, that is wrong. So the answer will be 4 only. Okay, so sorry. So coming to the next question, which among the following statements is or are incorrect? Okay, glycine has the largest side chain among all amino acids. Tryptophan and tyrosine are less polar than phenylalanine. Aspartate is a beta branched amino acid and histidine is a basic amino acid with an aromatic side chain. Which one do you think are incorrect? Which one do you think is incorrect? Glycine has the largest side chain among all amino acids, or tryptophan and tyrosine are less polar than phenylalanine, or aspartate is a beta branched amino acid, or histidine is a basic amino acid with an aromatic side chain. Which ones do you think are incorrect? Anybody? So, one or more of these statements can be incorrect. Which one do you think is incorrect? You have to explain that. So, the first three options will be incorrect. Lysine does not have the largest side chain among all amino acids. It is in fact the simplest amino acid. It has the smallest side chain, just a hydrogen atom in place of the side chain. So this statement is incorrect. Phenylalanine has a benzyl group which is nonpolar aromatic. Tyrosine has an OH group on the aromatic ring and a tryptophan has an indole NH group. Both make them more polar than phenylalanine. So this statement is also incorrect. Aspartate is a beta branched amino acid. That is incorrect because beta branched amino acids are valine, isoleucine, and threonine, where the branching occurs at the beta carbon. Aspartate is not beta branch, so this statement is also incorrect. However, the last statement is correct. Histidine is a basic amino acid with an aromatic side chain. It is an imidazole ring which is aromatic in its side chain and it can act as a weak base as well. So it is classified as a basic amino acid with an aromatic side chain. So this statement is correct. So the first three options were incorrect. So we already discussed about the backbone atoms of C alpha and C and O and N and O are the atoms of the backbone atoms of the amino acid. So the basic heart of the amino acid will be the C alpha group, to which are bound an amino group, a carboxyl group, and a hydrogen or the side chain. So for glycine, it is the hydrogen atom. For other amino acids, the side chains are more complex. So, if we could talk about the dipeptide, two amino acids can bind together to form the dipeptide with the release of one H2. So upon binding two protons from the NH chain, one oxygen from the carboxyl group will join to form a water. So the peptide bond has a one side a Cu and the other side an NH. Okay. So the amino acid sequence of the protein is the order of the amino acids in the protein chain. The sequence always read from the N terminus to the C terminus of the protein. There are many ways to characterize the properties of amino acids. The ones most useful and the most commonly used are hydrophobicity, size, charge, secondary structure preference, alcoholicity, aromaticity. And on top of that, there are some special characteristics like bridge forming by cysteines, rigidity of prolines, titrating at physiological pH of histidine, flexibility of glycines, etc. So amino acids are the molecular building blocks of proteins. Each amino acid has a carboxyl group and amino group, a side chain bonded to the alpha carbon atom. And the carboxyl and amino groups are combined in peptide linkage. In most body fluids, the carboxylic group and the amino group are ionized. And an ionized amino acid that has a positive and negative charge is a dipolar ion called as ion. Okay, you have the nonpolar side chains. Side chains clustered in the interior of the protein due to hydrophobicity. The side chain of proline. And its alpha amino group form a ring structure, and proline gives the fibrous structure of collagen and interrupts the alpha helices found in the globular proteins. In case of aromatic groups, side chains, they are non-polar, so that participate in hydrophobic interactions. Tyrosine is an important in some enzymes. Most proteins absorb light at a wavelength of 280 nanometer due to aromatic groups. Now, more hydrophilic because they form hydrogen bonds with water, the uncharged polar side chains. It includes serine, threonine, cysteine, asparagine, glutamine. Cysteine contains sulfhydryl group, an important component of the active site of many enzymes. Two cysteines can become oxidized to form a dimer, cysteine, which contains a covalent cross-link called a disulfide bond. The R groups have significant positive charge. Lysine has a second positive amino group at the position on its R chain. Arginine has a positively charged guanidino group. Histidine has a positive imidazole group facilitating the enzyme catalyzed reaction by serving as a proton donor or acceptor. So aspartic and glutamic acid are proton donors, and neutral pH side chains of these amino acids are fully ionized. They have a negatively charged carboxylate group at physiological pH. What are the uncommon amino acids? The hydroxylysine and hydroxyproline are found in the collagen and the gelatin proteins. Gamma carboxyglutamic acid is involved in blood clotting. N-methylarginine and N-acetyl-lysine are found in histone proteins. Now, if we talk about the optical properties of amino acids, the alpha carbon of amino acid is attached to four different chemical groups, is chiral or optically active carbon atom. Glycine is the exception. Amino acids exist in two forms, D and L, that are mirror images of each other. All amino acids found in proteins are of the L configuration. Now, acidic amino groups in aqueous solution contain weakly acidic alpha carboxyl groups and weakly basic alpha amino groups. Each of the acidic and the basic amino acids contain an ionizable group in its side chain. As both free and some of the combined amino acids in peptide linkages can act as buffers. So proteins can be classified based on the solubility and composition, function, shape and size. According to this classification, proteins are divided into three main groups as simple conjugation derived proteins. Simple proteins yield on hydrolysis only amino acids. These proteins are further classified based on the solubility in different solvents as well as their heat coagulability. Like albumins are readily soluble in water, dilute acids and alkalis and are coagulated by heat. Albumins may be precipitated out from solution using high salt concentration, a process called salting out. They're deficient in lysine. Okay, serum albumin and ovalbumin are examples. Now, globulins carry out synthesis, transport, and metabolism in the cells. They're insoluble and sparingly soluble in water, but the solubility is greatly increased by the addition of neutral salts such as sodium chloride. These proteins are coagulated by heat. They're deficient in methionine, serum globulin, fibrinogen, myosin of muscle, and globulins of pulses are examples. Histones are small and stable basic proteins. They contain fairly large amounts of basic amino acid histidine. They're soluble in water but insoluble in ammonium hydroxide. They're not readily coagulated by heat. They occur in globulin, hemoglobin, and nuclear proteins. Protamines are the simplest form of the proteins. They are soluble in water and are not coagulated by heat. They are basic in nature due to the presence of large quantities of arginine. Protamines are found in association with the nucleic acid in the sperm cells of certain fish. Tyrosine and tryptophan are usually absent in protamines. Prolamines are insoluble in water but soluble in 70 to 80% aqueous alcohol. Upon hydrolysis, they yield much proline and amide nitrogen, the same prolamine. Glutamines are insoluble in water and absolute alcohol but soluble in dilute alkalis and acids. They are plant proteins. Then we have albuminoids. These are characterized by great stability, insolubility in water and salt solutions. These are called albuminoids because they are essentially similar to albumin and globulins. They're highly resistant to proteolytic enzymes. They're fibrous in nature and form most of the supporting structures of animals. They occur as chief constituent of exoskeleton structures such as hair, horns, and nail. These are simple proteins combined with some non-protein substances known as prosthetic groups, the conjugated proteins. The nature of the non-protein or prosthetic groups is the basis for the sub-classification of conjugated proteins. Then we have the mucoproteins, which are composed of simple proteins in combination with carbohydrates like mucopolysaccharides, which include hyaluronic acid and chondroitin sulfates. On hydrolysis, mucopolysaccharides yield more than 4% of amino sugars, hexosamine and uronic acid. Soluble mucoproteins are neither readily denatured by heat nor easily precipitated by common protein precipitants like trichloroacetic acid or picric acid. The term glycoproteins is restricted to those proteins that contain small amounts of carbohydrate, usually less than 4% hexosamine. Then we have chromoproteins. These are proteins containing colored prosthetic groups, example hemoglobin, flavoprotein, and cytochrome. Lipoproteins, these are proteins conjugated with lipids such as neutral fat, phospholipids, and cholesterol. Then we have phosphoproteins, which are proteins containing phosphoric acid. It is linked to the hydroxyl group of certain amino acids like serine in the protein casein of milk. Then we talk about derived proteins. These are proteins derived by partial to complete hydrolysis from the simple or conjugated proteins by the action of acids, alkalis, or enzymes. They include two types of derivatives, primary derived proteins and secondary derived proteins. These protein derivatives are formed by processes causing only slight changes in the protein molecule and its properties. There is little or no hydrolytic cleavage of peptide bonds. Okay. We have secondary derived proteins which are formed in the progressive hydrolytic cleavage of the peptide bonds of protein molecule. They are roughly grouped into proteases, protons, and peptides according to average molecular weight. They are hydrolytic products of proteins which are soluble in water and not coagulated by heat. Peptones are hydrolytic products which are simpler structure than proteases. They are soluble in water and not coagulated by heat. They are composed of relatively few amino acids. They are water soluble and not coagulated by heat. Classification based on function will be enzymes, which are catalytic proteins. The most striking feature of these proteins is their ability to function within living cells as biocatalysts. These biocatalysts are called enzymes, which represent the largest class. Nearly 2000 different kinds of enzymes are known, each catalyzing a different kind of reaction. They enhance the reaction rates a millionfold. Then we have regulatory proteins or hormones, which are polypeptides and small proteins found in relatively lower concentrations in animal kingdom, but play a highly important regulatory role in maintaining order in complex metabolic reactions. Then we have contractile proteins. Proteins like actin and myosin function as essential elements in contractile system of skeletal muscle. Then we have secretory proteins. Fibroinase are proteins secreted by spiders and silkworms to form webs and cocoons. Protective proteins, antibodies. These proteins have protective defense function. These proteins combine with foreign protein and other substances and fight against certain diseases like immunoglobulin. These proteins are produced in the spleen and lymphatic cells in response to foreign substances called antigen. And the newly formed protein is called antibody, which specifically combines with the antigen which triggered its synthesis, thereby prevents the development of disease. Fibrin in the blood is also protective protein. Then it can be storage proteins like a major class of proteins which has the function of storing amino acids as nutrients and as building blocks for the growing embryo. Storage proteins are source of essential amino acids which cannot be synthesized by human beings. The major storage protein in pulses is globulins and prolamins in cereals. In rice, the major storage protein is glutalins. Albumin of egg and casein of milk are also storage proteins. We have transport proteins. Some proteins are capable of binding and transporting specific types of molecules through blood. Hemoglobin is a conjugated protein composed of colorless basic protein, the globin and protoporphyrin or heme. It has the capacity to bind with oxygen and transport through blood to various tissues. Myoglobin, a related protein, transports oxygen in the muscle. Lipids bind to serum proteins like albumin and transported to lipoproteins in the blood. Then we have toxic proteins. Some proteins which are toxic in nature. Ricin present in castor bean is extremely toxic to higher animals in very small amounts. Enzyme inhibitors such as trypsin inhibitor bind to digestive enzyme and prevent the availability of protein. Lectin, a toxic protein present in legumes, agglutinates red blood cells. Bacterial toxin causes cholera. It is a protein. Snake venom is protein in nature. Based on size and shape, the proteins are also subdivided into globular and fibrous proteins. Globular proteins are mostly water soluble and fragile in nature, like enzymes, hormones, and antibodies. They have compact spherical shapes. Fibrous proteins are tough and water insoluble. They're used to build a variety of materials that support and protect specific tissues. We'll not go into too much details of these. So classical, so if you want to find out the peptide structure determination, it's a amino acid sequence plus any disulfide links. Classical strategy will be Sanger. We determine what amino acids are present and their molar ratios, leave the peptide into smaller fragments and determine the amino acid composition of these smaller fragments. Identify the N terminus and the C terminus in the parent peptide and in each fragment, and organize the information so that the sequences of small fragments can be overlapped to reveal the full sequence. Amino acid analysis. Acid hydrolysis of the peptide gives a mixture of amino acids. The mixture is separated by annexation chromatography, which depends on the structures, on the differences in pI among the various amino acids that we discussed. Amino acids are detected using anhydrin automated method. It requires only a little amount of peptide. Now, acid hydrolysis of the peptide cleaves all of the peptide bonds, cleaving some but not all of the peptide bonds gives smaller fragments. These smaller fragments are then separated and the amino acids present in each fragment determined. Enzyme catalyzed cleavage is the preferred method for partial hydrolysis. The carboxypeptidase is a proteolytic enzyme. It catalyzes the hydrolysis of proteins. Carboxypeptide is selective for cleaving the peptide bond to the C-terminal amino acid. Trypsin is selective for cleaving the peptide bond to the carboxyl group of lysine or arginine. Chymotrypsin is selective for cleaving the peptide bond to the carboxyl group of amino acids with an aromatic side chain like phenylalanine, tyrosine, and tryptophan. How do we do the N group analysis? Amino acid is sequence is ambiguous unless we know whether to read it left to right or right to left. We need to know what are the N terminal, C terminal amino acids are. C terminal amino acid can be determined by carboxypeptidase catalyzed hydrolysis. Several chemical methods have been developed for identifying N terminus. They depend on the fact that the amino N at the terminus is more nucleophilic than any of the amide nitrogens. We have Sanger's method where the key reagent is Sanger's ester N terminus is 1-fluoro-2,4-dinitrobenzene, and it's a very reactive towards nucleophilic aromatic substitution. It reacts with the amino and nitrogen of the N terminal amino acid. Acid hydrolysis cleaves all of the peptide bonds, leaving a mixture of amino groups, only one of which N terminus bears a 2,4-DNP group. Okay. So insulin, like for example, it's a polypeptide with 51 amino acids. It has two chains called the A chain and the B chain. Now, how was it the B chain of bovine insulin? Phenylalanine N terminus, pepsin catalyzed hydrolysis gave the four peptides. So overlaps between the above peptide sequences are found in the four additional peptides. So trypsin catalyzed hydrolysis gave this, which completes the sequence. This is how the sequence was determined. The sequence of the alpha chain was determined using the same strategy, establishing the disulfide links between the two cysteine and residues completed the primary structure. Now, the Edmond degradation is method for determining N-terminal amino acid can be done sequentially, one residue at a time on the same sample. Usually, one can determine the first 20 or so amino acids from the N terminus by this method. Very small amount is sufficient. The key reagent in the Edmond degradation is phenyl isothiocyanate. Phenyl isothiocyanate reacts with the amino nitrogen of the N-terminal amino acid, and the product is this. The PTC derivative is then treated with HCl in an iron hydride solvent, and the N-terminal amino acid is cleaved from the remainder of the peptide. So the product is thiazolone under the conditions of the formation. The thiazolone reacts to a phenyl thiohydroentine derivative. Okay, so we'll not go into more details. We have talked about all of these. Primary, secondary, tertiary, and quaternary structure. Quaternary is basically the spatial arrangement of multiple polypeptide chains known as the subunits. It can act as enzymes like catalase, hormones, regulation, storage for bioreserve, transport for transporting substances, structural for providing shape, protective bodies, defense, contractile work or motion. Okay, so we'll not go into details of these. We already know about the polar, non-polar, aromatic and non-aromatic amino acids. Just the R groups. We have talked about all of these acid-base chemistry. Okay. So coming back to the question that we started with, among the four statements, the first three are incorrect, the fourth one is only correct. Anybody has any questions regarding this? Anybody has any question? If nobody has any question, we can stop the session today and we'll meet again next Monday, same time. Okay, so if nobody has any question, we'll stop today's session over here. And I'll upload these sessions on YouTube and we'll meet again next Monday. Thank you. Thank you, everyone.